In this video, I'm going to talk about polar coordinates. And before we dive into the topic of polar coordinates, let's take a look at our motivation, why we need to study this. So the first reason why we're going to study this is we want a different way to represent a point in the plane. So we want a different way to do that. It's always nice to have multiple ways to do something. It gives us different options. And so far we've been graphing points in rectangular plane using two values, x and y values. So for example, if I want to plot this point P, I need to know two things. I need to know the horizontal distance from the origin, and I also need to know the vertical distance. So for example, I would go horizontally x units here, and I would go vertically y units to get to that point. Okay, so that's one way we've been plotting points in the plane. What we want now is a different way of doing the same thing. We want to represent a point in the plane, some point P, but instead of using horizontal and vertical distances, we want to use a different concept. And that's going to, so like for example, this point now, instead of using a horizontal distance and a vertical distance, instead of using two distances, what I want to do is I want to write this point using radius, using a distance, and an angle. So that's what I want to be able to do. This is rectangular coordinates, and this is what we'll call in a little bit polar coordinates. So it just gives us a different way to write a point. Instead of using two distances, we might write it using a distance and an angle. Okay, and that might be beneficial in some cases. So that's our second reason. Basically, changing coordinate systems by that I mean is going from rectangular coordinates to polar coordinates. Okay, so changing coordinate system makes some problems easier. So our two motivations are, one is we just want to have a different way to write a point in the plane, just a different representation. Instead of using two distances, we want to use a distance and an angle. The second motivation is some problems are much easier to do in polar coordinates in a different coordinate system than in rectangular coordinates. And let me show that to you by doing an example. Let's say I want to find the area of a circle of radius 2. This is a very trivial problem, but let's see how we would do this in calculus. Okay, we know the answer is going to be, area is going to be 4 pi. Okay, now if I wanted to do this problem in calculus using rectangular coordinates, okay, I would start with something like this. I would start with a circle of radius 2. So this is in rectangular coordinates here. This is 2. And this equation in rectangular coordinates is given by x squared plus y squared is equal to 4. And if I wanted to find this area, I would first start by finding this area from 0 to 2 and multiplying that by 4 to get the area of the circle. So this is the top half of my circle, and to get to that I would have to solve this equation for y. So let's do that. So we get y squared is equal to 4 minus x squared. So that gives us y is equal to plus or minus square root of 4 minus x squared. So we started with this, x squared plus y squared is equal to 4, and we isolated y. The negative radical gives us the bottom half of the circle, this part, and the positive gives us the top half of the circle. Since we want to find this area in the first quadrant, we're going to use the positive one. Okay. So in our case, this piece here, color it blue, that piece is given by y is equal to square root of 4 minus x squared. Okay. Now, how do I find the area? Well, the formula for area in calculus is the integral from a to b f of x dx, where f of x is your curve and curve that you're working with, and you're trying to find the area under that curve. In our case, we're going to go from 0 to 2, because we're going to integrate from 0 to 2, and my curve, like I just told you, is the square root of 4 minus x squared dx. So that is the formula for area. Now, to solve this integral, it's not a trivial integral. It's not a known integral. We cannot do term by term, but it is a composite function. If you were to substitute for the inside, you would notice you wouldn't make any headway. And then you cannot rewrite it any further. You can't do any other type. We have to try other substitutions. In this case, the other substitution we're going to try is this one. We're going to go let x is equal to 2 sine theta, and then we go dx is equal to 2 cosine theta d theta. So our problem reduces to this now, 0 to 2. We get square root, so we're going to replace that. So we get square root of 4 minus 4 sine squared theta, and then dx becomes this, 2 cosine theta d theta. And then we can change these limits of integration. So we know that over here, this limit represents x. Okay, you can see that. So if x is 0, so we get 2 sine theta is equal to 0. So sine theta is 0. So theta must be 0. Okay. And if I were to use this limit, if x is 2, in the same substitution, 2 is equal to 2 sine theta. So we get sine theta is equal to 1. So theta is equal to pi over 2, because sine of pi over 2 is 1. So I can integrate to pi over 2 then. So now I have 0 to pi over 2. I can pull out a 4, square root of 4 is 2, and I'm left with 1 minus cosine squared theta, 2 cosine theta d theta. The 2 and the 2 can be multiplied to a 4, and in the first, this will become sine squared cosine theta d theta. Oops, this should be, sorry, I'm getting ahead of myself. This should be sine squared theta, and this will become cosine squared theta. Now, in the first quadrant, cosine is always positive, so when we take the square root of cosine squared, we just get cosine. Now, this will give us this integral, 0 to pi over 2. And this is cosine squared theta d theta. Now we'll have to use a double angle identity. If you recall, cosine squared theta is 1 plus cosine of 2 theta over 2, and then you'll have to do term by term integration. Then you'll have to plug in the upper limit and the lower limit, and you can see this problem has gotten out of hand. Okay, well, let's try to do the same problem in polar coordinates. Well, we'll start with the same thing. We'll start with a circle. The nice thing is, this is the equation of the circle in rectangular coordinates. It's the same equation in polar coordinates, is just r is equal to 2. Okay, so that's what we're going to start with. The formula for area in polar coordinates is this, a to b, it's 1/2, sorry, 1/2 the integral a to b of r squared d theta, where r is this. Well, let's take a look at that. So in our case, r is 2, so we get 1/2 the integral of 4 d theta. What is theta now? What are my limits? Sorry. The limits have to do with theta. So if you start here, my angle theta is 0, and you're going to go all the way around and then come back here. So my angle theta will be 2 pi. So I'm going to integrate from 0 to 2 pi. Okay. So if I do that, this will become a 2, and the 2 will come out. So we're just integrating 1, which will give us 2 theta from 0 to 2 pi. And when I plug in the upper limit, I'll get 4 pi. And when I plug in the lower limit, I'll get 0. So the answer is 4 pi. And you can see this problem was much easier to do in polar coordinates. And this is just one example of many that you will see in Calculus 3. So polar coordinates are very essential because they make certain problems very easy. And they also give us an ability to write a point using a different notation. Instead of using 2 distances, we're using a distance and an angle. So let's learn how to do that. Okay. So here's polar coordinates. Okay. So typically in polar coordinates, we have a very similar plane, but we don't have x and y, really. We call this the pole. The origin is called the pole. The positive x-axis is called the polar axis. Okay. And so a point in the plane now, any point in the plane, so let's call this point P, is now represented by 2 values. One is the distance r, and that distance is the distance from the pole to the point, so that's this distance. Okay, and the other value is the angle measured from the polar axis. So that's this angle here, theta, the counterclockwise measure. Okay, so every point now is going to be represented by 2 values. Okay, the best way to graph something is measure the angle first and then diagonally go whatever the length r is. Okay, so out here we can say where theta is measured counterclockwise, and r is a directed distance. What by that I mean is it can be negative. Okay, so that's what polar coordinates are. Usually there's special paper that people use to graph curves in polar coordinates, but you don't really need it. But if you're interested, you can find some on my L drive, or you can Google it and you can find a special polar paper. You can just Google polar paper. Okay, the polar paper looks like this. You have, this is theta is 0, theta is pi over 2, theta is pi, theta is 3 pi over 2, and then it has concentric circles for different values of r. So this would be circle for r is 1, this would be a circle for r is 2, and so on. So this is what the polar paper looks like. And then it also has, so it has concentric circles for different values of r, but I'm going to use that for. And then it also has certain angles, certain common angles drawn out for us. So this one exactly in the middle is theta is pi over 4. Then they have theta is pi over 6. Then we have theta is pi over 3, and so on. There's certain common angles, and you can do that similar things for certain common angles in quadrants 2 and 4. I've only done it for quadrants 1 and 3, but we can do that. That's what a typical polar paper looks like. Okay, but let's go ahead and, while we are doing this, let's go ahead and graph. I'm going to get rid of some of this stuff. Let's take a look at how to graph points on the polar axes, on the polar paper, graph paper. So let's say I want to do this. We want to graph these points here. So I'm going to write down a whole bunch of points and then we'll graph them and see what they look like. So P is going to be 3 pi. Q is going to be 3 times 3 pi. R is going to be 1 minus pi over 2. S is going to be negative 3 and 2 pi. Okay. T is going to be 2 and pi over 4. And let's do one more. U is going to be negative 1 and pi over 3. Okay, let's actually, so let's graph these. So let's take a look at P. Well, to graph P, remember this is R, this is theta. Start with the angle first and then go along the concentric circles till you get to 3. So pi means you're going 180 degrees, so we are here somewhere on this line. And then on that line, we're going to go 3 units from the pole. 1, 2, and 3. So this is point P. Okay. Let's take a look at Q. Q is 3 and 3 pi. That means you're going to go all the way around once. That'll be 2 pi. Then you're going to go pi more. We're back on this line again. You're going to go 3 units on that line from the pole. We're back to here. Q. Right away, we see something really different when we talk about points in polar coordinates. If you think about it, points in rectangular coordinates have only one representation. There's only one way to represent this point P in rectangular coordinates. If, let's say, x was 2 and y was 1. There's only one way to do that, 2 and 1. This is the only point in rectangular coordinates that can be written as 2 and 1. So points in rectangular coordinates are unique. But if you look at polar coordinates, points are not unique because we wrote the same point, this point, as P and as Q, and they're two different values. Okay, so that's one thing you should take away right away. So let me put that down as a big note. Note, points in polar coordinates are not unique. In rectangular coordinates, points are unique, but in polar coordinates, they're not unique. So there's actually infinite ways to write points in polar coordinates. Okay? Let's take a look at one more. R, you're going negative pi over 2, so you're going clockwise pi over 2, and then once we get there, so we'll get here, and on the 3 pi over 2 line, we're going to go 1 unit from the pole, so that's this point here. So that's R. How about negative 3 and 2 pi? Well, let's go the angle first. We go all the way around. We're back on this line. Okay, but now we're going to go negative 3 units. Anytime R is negative, we basically flip and go 180 degrees in the opposite direction. So instead of being on this line now, because R is negative, we're going to flip and we're back to this line and we're going to go 3 units on that line. Okay, so if I go 3 units on that line, I'm going to get 1, 2, and 3. That's this point. So this is again S. So again, this point, this, and this, they're exactly the same points, just written differently using 3 different values. Okay. Let's take a look at T. T is 2 and pi over 4. So we're going to go pi over 4, go to the pi over 4 line, which is this guy here. And on that line, we're going to go 2 units from the pole. So we have 1, 2. So this point here is T. Similarly, U is negative 1 and pi over 3. So we're going to go to the line that is pi over 3 here. And on that line, we have to go negative 1 units. But remember what I just said. If R is negative, then we flip 180 degrees. So we'll go all the way on this line. That's exactly 180 degrees from here. And then we're going to go 2 units on 1 unit on that line. So that's this point here. So that's going to be U. So anytime R is negative, you just flip 180 degrees and that'll give you the point there. So now that we know how to plot points in polar coordinates, because we're eventually going to be switching coordinates, we need to know how to go from one coordinate system to another, how to switch back and forth. So let's take a look at that. Switching coordinates. Switching between polar coordinates and rectangular coordinates. So how do we switch between the two coordinates? Okay, so let's take a look at that. Alright, so I'm going to start first by going from rectangular coordinates to polar coordinates, and then we'll go from polar coordinates to rectangular coordinates. Okay, so let's take a look at it. Well, in both cases, we're going to start with the same picture, so let me put that picture in the middle. So let's say I have this. So I have some point here, P. This is R. So it's X and Y because we're in rectangular coordinates right now. I want to switch to polar coordinates. Well, how do I do that? Well, let's take a look at it. This angle would be theta, let's call that. This is a 90-degree triangle. Okay. This distance from the origin to here is X, and this is Y, the vertical distance. From trig, we know that cosine of theta is equal to opposite over hypotenuse. Okay. Oops, I'm sorry. I want to go from rectangular to polar first, so I'm getting ahead of myself. So if I'm going to change it to polar coordinates, I need to find R and I need to find theta given X and Y, because you're given something in rectangular coordinates and you want to switch it to polar. If you look at that triangle using the Pythagorean theorem, we get what? R squared is equal to X squared plus Y squared. So we get R is equal to plus or minus square root of X squared plus Y squared. Remember, R can be negative, that's why we have plus or minus there. Now to find the angle, we use trig. We know that tangent theta is equal to y over x. The reason why I'm using tangent is, remember, because we're given x and y. So we're given this, and I want to find the angle. So it tells me theta is equal to tan inverse of y over x. Okay? So that gives us a nice way to switch between rectangular to polar. So let me write that down. R is equal to plus or minus square root of x squared plus y squared, and the angle theta is tan inverse of y over x. Okay. So this is to go from rectangular to polar. Let's do the same thing now here. So now I'm given something in r and theta, and I want to change it to x and y. Okay. So let's do that. So if you think about it, how do I relate? Because I'm given theta and r, so I want to relate this side now with this and this. Using trig, I know that cosine theta is equal to adjacent over the hypotenuse. That tells me x is equal to r cosine theta. And similarly, sine theta is equal to y over r. So that tells me y is equal to r sine theta. So it's really easy to go from polar to rectangular. X becomes r times cosine theta, and y is equal to r times sine theta. Okay. That's to switch from polar to rectangular. So let's take a look at some examples and see how to do them. Okay. Let's start with something easy. So let's say if you're given r theta, which is 2 and pi over 4, and we want to change this point to rectangular coordinates. So we're given something in polar coordinates, we want to change it to rectangular coordinates. If you remember, the formula is what? X is r cosine theta. So we get 2 times cosine of pi over 4. So we end up with square root of 2. And y is equal to r sine theta, which will give us 2 times sine of pi over 4, which is also going to be square root of 2. So the point in rectangular coordinates that's the same as this point is going to be square root of 2 and square root of 2. Okay. Now let's go the other way. So let's say if I'm given this point, okay, I'm given let's take 1 and square root of 3, and I want to change that to polar coordinates. So this is x and y. So this is given to us in x and y, and we want to change it to polar coordinates. Okay, so let's do that. So to change to polar coordinates, I need to find r first. So if you recall, r squared is equal to x squared plus y squared. This is x and y. So we get 1 plus 3, which gives us 4. So we get r is equal to plus or minus 2. Now you'll have to decide which sign you want to use, and we'll take a look at that. And the angle theta is given by tan inverse of y over x. So it's going to be tan inverse of square root of 3. Well, tangent of tan inverse of square root of 3 is pi over 3, 60 degrees. Okay, so we get that. So now if you look at this point, these are both positive, so you're in the first quadrant. So in the first quadrant, if I go pi over 3 radians, and then go 2 units, I'll get that. So like, think about it. If I go, let's say this line here is theta is equal to pi over 3. So I'm going to go to that line, and then on that line I'm going to go 3 units from the pole. So that's 1, 2, 3. So that's this point here. Okay? So that's this point that's given to us. Now if I use the positive 2, if I use negative 2, then remember what will happen. You flip and go 180 degrees. You get 1, 2, and 3. So this point here would be negative 2 and pi over 3 in polar coordinates. And this point here would be 2 pi over 3. So we want this point because we want the point in the first quadrant. So our point in polar coordinates here is going to be 2 pi over 3. Okay. Now we also want to have the ability not just change points from one coordinate system to the other coordinate, we also want to be able to change equations from one coordinate to another coordinate. So let's take a look at that. Okay, so let's start with just initially changing what we want to start with, changing our rectangular coordinate equations to polar coordinates. So let's say if I give you this. So in this case, we're going to change from rectangular coordinates to polar coordinates. So let's take a look at the first example. Let's say we have x squared is equal to 8y. Now this is in rectangular coordinates, but I know x in polar coordinates is r cosine theta, so I get r cosine theta squared is equal to 8, and y is r sine theta. So I get r squared cosine squared theta is equal to 8r sine theta. We'll divide both sides by r, so we get r cosine squared theta is equal to 8 sine theta, and divide by cosine squared, so you get 8 sine theta over cosine squared theta. Now this is a fairly good representation, but I can write it a little bit nicer. 8 tangent theta secant theta. So that this polar equation, is the same as this rectangular equation. Okay. So we can always switch between one coordinate system into another by making the appropriate substitutions. Let's take a look at one more example. So let's say if I have this, we have, let's say we have x squared plus y squared minus 4xy is equal to 0. And I want to change this to polar coordinates. Okay. I know that x squared plus y squared in polar coordinates is r squared, so I can exploit that right away. Okay. Minus 4, oh, I'm sorry, this should be, let's make these cubes. Okay, so we get r cubed cosine cubed theta plus r cubed sine cubed theta minus 4x is r sine theta, cosine theta, sorry, and r sine theta is equal to 0. Okay, I'm going to move this term to the right hand side of the equality, and I'm going to factor out the r cubed here. So we get 4r squared cosine theta sine theta. I multiplied these r's here. I can cancel this with this. So I get r is equal to 4 cosine theta sine theta divided by cosine cube theta plus sine cube theta. So this is the value of r. Okay. So this polar rectangular equation is the same as this. So that's how we change from rectangular to polar coordinates, but once again we can also do the other way around. So let's take a look at that. So let's say I want to go from polar coordinates to rectangular coordinates now. So now these become a little bit more fun to do. So let's take a look at some of these. So let's say if I give you this r is equal to negative 4 secant theta. So let's take a look at that. Well, I know that secant theta is the same as 1 over cosine theta. I can cross multiply. So I get this. So r cosine theta is the same as x. So we end up with this. So this is the equivalent equation in rectangular coordinates for this one. Basically a vertical line. Okay. 2. Let's say we have r is equal to 4 over 2 cosine theta minus sine theta. Okay. So let's take a look at that. So in this case I can cross multiply again. So I get 2r cosine theta minus r sine theta is equal to 4. Okay, as soon as I do that, we know something right away, correct? What do we know? We know that r cosine theta is x, r sine theta is y is equal to 4. So we get y is equal to 2x minus 4. So we get a line. Out here we get a vertical line. Out here we just get a diagonal line with slope 2. And these polar equations are much more complicated compared to what we end up with in rectangular coordinates. Let's do maybe 2 more examples of that. So let's say if I give you r is equal to 9 cosine theta. Okay. So how do I change this? What is this equivalent to in rectangular coordinates? Well, what I'm going to do is multiply both sides by r. So I get r squared is cosine theta. Okay. Now I can replace r squared with x squared plus y squared, and r cosine theta with x. I'll move that x to the opposite side. Okay. And then we'll complete the squares for this. So I'm going to add. Okay. Over here, let me go ahead and use a different number so then the math becomes a little bit easier. So I'll make it a 10 instead of a 9. Actually, it'd be easier to change it to an 8, so that way you guys don't have to erase everything. So just make this into an 8. So I'm going to add a 4, and I'm going to subtract a 4 plus y squared is equal to 0. So we're completing the square, so these 3 terms can be written as x minus 4 squared plus y squared is equal to 4. I'm going to move this 4 to the other side. So this is really the same as this equation. So this time, the polar equation is a lot easier than the rectangular equation in terms of difficulty, but this happens to be a circle, which is of radius 2. and has a center at 4 and 0 and radius 2. Okay. So that's how we change that one to polar to rectangular coordinates. So out here we did completing the squares. Let me do one last example of this. So let's say if I have 4, let's say we have r squared sine of 2 theta. Well, let's do this. I have r squared is equal to 4 cosecant of 2 theta. Okay. Well, let's try to rewrite this. We have 4 over sine of 2 theta because cosecant is 1 over sine. But then we have a nice identity for sine, which is sine theta and cosine theta. And we do want to change that because if you recall, the relationship between x and y has to do with just theta, not with a double angle. You know that this is x. It's not r of cosine of 2 theta is x. That's not what it is. Okay, so we always want to change those double angles to single angles right away. I'm going to cross multiply and I'm going to reduce this. So I get r sine theta times r cosine theta is equal to 2. So I split this r into 2, r and r, and then I multiplied these. The reason for that is because this is y now, and this is x is equal to 2. So y is equal to 2 over x. Okay, so that's how we get that. Okay, so those are some examples of switching between equations between polar and rectangular coordinates. Okay, all you have to do is just massage them enough till you get it to a form that you're happy with. Okay, so just make sure you do that. All right, the next thing we're going to do then is we're going to go ahead and actually take a look at how to graph these equations in polar coordinates. So we have D, graphing polar equations. Okay. Now before I do that, before we talk about graphing polar equations, let's just quickly talk about symmetry, because that'll make it a little bit easier to graph if you check the symmetry, and if you don't, that's all right, but it will make it a little bit easier to graph. Is that okay? So let's take a look at that. So we'll talk about symmetry in polar coordinates. So the first thing is we can say that a curve in polar coordinates is symmetric with respect to the x-axis if replacing theta by minus theta, okay, does not alter the equation. Okay, it's symmetric with respect to the x-axis when that happens. So let's take a look at it visually and then I'll do an example. So what does that mean? That basically means this. So if I have a point here P, which is r theta, okay, that means that we're talking symmetric with respect to the x-axis, so there's another point here. Okay, I'll call it P prime, and that's going to be what? In this case, it will be r negative theta. Okay, so a curve is symmetric with respect to the x-axis. If you replace theta with minus theta, it doesn't alter the equation. So in this case, this is this point, this is this. What does that mean? Let's take a look at this curve. R is equal to 2 plus 2 cosine theta. So what we're going to do here is we're going to change theta to minus theta, and if the curve remains the same, then we say that this curve in polar coordinates is symmetric with respect to the x-axis. Whatever we have here, we're going to have down here. Okay, so let's do that. R is equal to 2 plus 2 cosine of minus theta. But we know from trig cosine is an even function, so cosine of minus theta is just cosine theta. So you can see we are back to the original equation that we started with. So that tells me that this curve is symmetric with respect to the x-axis. And if you were to graph this curve, if you were to graph it, we'll learn how to do that in a second, you'd notice that the graph looks something like this. So you can see whatever we have on the top here, above the x-axis, we have that on the bottom. So we say that that curve is symmetric with respect to the x-axis. So that's one way we can talk about symmetry. Another way we can talk about symmetry is this. We can say a curve in polar coordinates is symmetric about the y-axis if replacing theta by pi minus theta, okay, does not alter the equation. Okay, so what does that mean graphically? So let's take a look at that. Okay. So let's say I have this point here, P. This is r theta. And if you think about it, what is this angle here? This angle is pi minus theta if this is theta. So this is my point P prime, and the coordinates of that are r pi minus theta. Okay, so that's the same point. Not the same point as P, but it's the point reflected about the y-axis of P. That's what I mean. Okay, so you reflect this point this way. So what does that mean in terms of, an example? Let's do an example. Okay, so let's say that I have r is equal to, okay, we have about the cosine of 2 theta. So now we're going to change theta to pi minus theta and see if it gives us the original equation back. So get r is equal to cosine of 2 pi minus 2 theta. So I'm replacing the theta with this and distributing the 2. Now we'll use a trig identity. So we get cosine of 2 pi, cosine of 2 theta, plus sine of 2 pi, sine of 2 theta. Excuse me. We know that sine of 2 pi is 0, so that whole thing is gone. Cosine of 2 pi is 1, so we get r is equal to cosine of 2 theta. So we are back to the original problem that we started with. So that tells me that this curve is symmetric about the y-axis. So whatever we have on the right of the y-axis, we'll have on the left. So let's take a look at a graph of this. So if you were to graph this, it actually looks something like this on the right. Excuse me. And if you were to, because this is symmetric about the y-axis, whatever we have on the right, we're going to have on the left. So that's what that graph looks like. All right. There's one last symmetry. Excuse me. All right. So the last symmetry that we're going to take a look at is a curve in polar coordinates is symmetric about the origin if replacing r by minus r does not alter the equation. Excuse me. Alright, so what does that mean graphically? So if you have a point here P, which is r theta, if I replace this r with minus r, what point would I get? Remember what I said, you go 180 degrees in the opposite direction. Go 180 degrees and then go r units in that direction. So this would be the same point here. I'll just draw it too far out. So this would be P prime, which is minus r theta. Now that's symmetric about the origin. Okay, so let's take a look at an example of something like this that's symmetric about the origin. So let's say we have r squared is equal to 2, so let's use 4 sine of 2 theta. So what are we going to do? We're going to change r to minus r, so we get negative r squared is equal to 4 sine of 2 theta. We're not doing anything with thetas, so we get r squared is equal to 4 sine of 2 theta. You can see we back to the original problem we started. Now if you were to graph this, it looks something like this. So if you were to graph just part of the curve out here in the first quadrant, we get that. But because this curve now is symmetric about the origin, whatever we have up here, we're going to have down here because of property. So we'll get the opposite. So it's basically the infinite symbol is what it is. Okay, except it's diagonal. So that's what this curve looks like. Alright. So now we know something about symmetry, and you can use that, or you cannot. In some problems, that may make it easier, quicker to graph. But even if you don't use symmetry, you can graph most polar curves without symmetry too. Okay. So the next thing we're going to take a look at is graphing polar curves. Okay. So we looked at symmetry here. So how to graph polar equations. Okay, there's 3 ways we can do this. One is by brute force, which is usually not the best way to do. By brute force, I mean we just start picking different values of theta, plugging it into the polar equation and finding r, and then plotting the points and doing that, which is extremely tedious. Okay. The second method is by changing the polar equation to rectangular equation. By that I mean doing what we did up here. Like what we did, right? Ugh, scroll bar just doesn't want to cooperate. So what we did here when we went from polar equations to rectangular equations, like this. Okay, so that's what we want to do. Okay. All right. So that's the second option, but again, that's not feasible. Sometimes you cannot do that. It's hard to do, or to change it to rectangular equations, or we might end up with a rectangular equation which is very complicated too. Okay, so that's not that causes problems. The third option is to use the theta r plot. Okay, so then the third option is we can use the theta r plot to help us graph the curve. So this is usually one of the nicest ways to graph because we know how to graph in 2 dimensions, so that makes it easier. The other 2 methods are not as easy to work with, but let's do an example with all 3 methods so you guys can see that. So let's say if I ask you to graph r is equal to sine theta. Okay, The first thing I'm going to do is check for symmetry just because we just talked about it. Like I said, you don't have to do that. You can still graph without it, but let's do that. I'll do it on the side here. I'm going to change theta to negative theta to check to see if it's symmetric about the y-axis. Okay, I'm sorry, x-axis. So we get r is equal to sine of minus theta. Okay, remember sine is an odd function, so you'll end up with negative sine theta, and that isn't what we started with. So this tells me it's not symmetric about the origin. Okay, I'm sorry, it's not symmetric about the x-axis. Okay, that's what we just did here. Let's see, just to make sure I don't goof you guys up. We did this. We changed theta to minus theta. So we talk about symmetric about the x-axis, which it isn't. The next thing I can try is change theta to pi minus theta and see what happens. So let's do that. So we get sine of pi minus theta. Once again, I'm going to use a trig identity. I get sine of pi cosine theta minus sine theta and cosine of pi. I know from trig that sine of pi is 0, so this whole thing is gone. We know from trig that cosine of pi is minus 1. There's a negative in the front here, so that'll make it positive, so you'll just get sine theta. So that's good. What does this tell us when we do this and we still get back the same equation we started? So this tells us that this graph is symmetric about y-axis. So whatever we have on the right, we have on the left. So if we can plot the right side, we'll be able to plot the left then. Okay. So let's utilize that. So the first method we're going to use is brute force. So by that I mean we're just going to pick some thetas, and we'll pick the nice angle 0, pi over 6, pi over 4, pi over 3, pi over 2, and so on, and we'll find r. So sine of 0 is 0, sine of pi over 6 is 1/2, sine of pi over 4 is square root of 2 over 2, then you get square root of 3 over 2, and then you get 1. Now I'm going to stop here because I want to see what happens so far. Okay, 0, 0, that's this point. What does this mean? That means you're going to rotate by an angle of pi over 6, and along that ray you're going to go half a unit up. So imagine this is pi over 6, this is pi over 4, this is pi over 3. On this line I'm going to just go half a unit up. What does this mean? On the line pi over 4, you're going to go square root of 2 over 2, which is 1.4 divided by 2. So it'll be 0.7 units. So you're going to go a little bit further out. And same thing for this one, it's 1.7 over 2, so it's going to be 0.85 roughly. So you're going to, on the pi over 3 line, you're going to go further out, okay? And then at pi over 2, you're going to be at 1, okay? So you can see we're going to get something like this. Well, because of this fact, it's symmetric about there, I know the other half is going to be the same. And if I had drawn it to scale, you would notice that we would end up with a circle of radius 1/2. Okay, so that's what that graph looks like. Okay, so always remember that when you have r is equal to sine theta, it's just a circle about the x-axis of radius 1/2. That's one way to do that, which again I didn't spend too much time on because I do not want you to do problems with brute force, but you can always use brute force to check your work. Okay, and in some cases, if the problems are really super difficult, you can try brute force to help you out too. The second option is we're going to change the polar equation to a rectangular equation. We can try that. And again, the reason why I don't like this is sometimes the rectangular equation will be more complicated and sometimes it will be really hard to change it too. So it's better to, we got to go by each problem. If it's easier to do, then you can try that. But let's try this one. So we have r is equal to sine theta. I'm going to multiply both sides by r. Get this. r squared, if you remember, is x squared plus y squared, and r sine theta is y. And I'm going to move the y terms to the other side, becomes 0. I'm going to complete the squares for y now. We did that earlier, so we're going to do the same thing. I'm going to add a half, and I'm going to subtract a half is equal to 0. I'm sorry, we're going to add a fourth, and I'm going to subtract a fourth. Now these three terms can be written as a square, so we get x squared plus y minus 1/2 squared is equal to 1/4. I'm going to move this to the other side. If you recall from algebra, you should recognize this. This is a circle centered at 0 because there's no displacement in the x direction, but in the y direction it is 1/2. And the radius is the square of r squared is equal to that, so the square root of that is 1/2. Okay. So if you were to graph it, my radius, this should be a plus, sorry, because there's a minus here. So if this is 1, so here is my center, and my radius is 1/2. You can see that this is 1/2 here. So we're going to draw a circle. So there is your graph. So this one, we were able to change it to rectangular coordinates and graph the corresponding rectangular equation, which was just the equation of a circle because we recognized it, right? The third way to graph is to use the theta r plot. What does that mean? Well, what that means is you treat this polar equation, you treat this as y and treat this as x and plot it, just like you would an x and y equation. So this is basically just a sine curve. I'll draw one period. It's 2 pi. Okay, so this is pi over 2, 3 pi over 2, pi. So now the key thing to remember is this now is r, because r is acting like a y, and this is theta. So that's what I meant by theta r plot. So you just basically plot this on a rectangular, in rectangular coordinates. You treat r and theta as x and y and just plot it. And then use that to graph your polar curve, sorry. So this is my polar curve now. Okay. So how do I do that? Well, just take a look at what's happening here. You're starting at 0 at the origin. So you're starting at the pole here. And then what's happening? As the angle increases, your r values are getting bigger also. And they're peaking at pi over 2 and 1. The other thing you could do is there's some key points here. There's a key point here. I know it's pi over 2 and 1. So that's 1. Then the other key point here is this one. That's 3 pi over 2 and minus 1. So I would, if you want to go to 3 pi over 2, you get here, this is 3 pi over 2. But minus 1 means what? You're going to go 180 degrees, so you're going to be back to this point. So this point basically is for both. So this is minus 1 and 3 pi over 2, and it is also 1 and pi over 2. So it's the same point. Remember, polar points are not unique, so we get that. And at pi, r is 0, so we are back here, pi. So if you go to pi units, you don't go anywhere on that line. You just stay at the pole. Okay. So let's see what's happening. So we know that it peaks here. So as the angle increases, r increases and peaks at 1 at pi over 2. So you can see as the angle increases, okay, r will increase, will go further out, peak here. Okay. And then what happens? As the angle keeps increasing, r decreases and goes to 0 at pi. Remember, at pi we already established it was 0. So come back to 0. Okay. Then in here, when you're in this quadrant, you're in quadrant 3, that's this. What is r doing? R is negative. Because r is negative, instead of being in this quadrant, it's going to flip and go 180 degrees to the opposite side. So you'll get this piece again. And then it's still negative. So when you're in this quadrant in Q4, R is still negative. You can see it's below the x-axis. So that'll again flip and go to the other side, so you'll get this piece again. So basically, you're going to make from 0 to 2 pi, you're going to make 2 revolutions here of the same circle. Okay, so you can use the r theta plot, just see what's happening as theta is increasing. What's r doing? It's getting bigger, then it peaks, then it gets smaller, and then it becomes negative. When it becomes negative, it flips and goes to the other side, so you can use that fact to help you out. Okay, all right, let me do one more example of that, how to use r theta plot, and then we'll be done. Okay, with plotting at least. Sorry, not done with the video. But so let's say if you want to plot this, r is equal to cosine of 2 theta. Earlier we found out that this is symmetric with respect to the y-axis. So it's just like this graph, symmetric by the way is with respect to the y-axis, so is this one. But this time I'm only going to use the r theta plot to do it. So let's plot this in r and theta. So this is theta, this is r. So you just treat this as your y and this is your x and graph it on your calculator. So we get, it's going to go down, it's going to go up. Basically, it's going to make two cycles from 0 to 2 pi. This is 2 pi. This is pi, pi over 2, pi over 4, and so on. This is 1 minus 1. Okay. So let's see what happens with the polar curve. So when the angle is 0, we start at 1. So this is 0 angle, we start at 1 here. Okay. All right. Let's take a look at some key points here. At pi over 4, it's going to be 0. So this is my line, pi over 4. One of the things I'm going to show you later is anytime for whatever angle, if r becomes 0, then that curve comes tangent to that angle line. So it's not going to come like this. It's going to come actually tangent to that line. Okay, so let's see, just take a look at that piece. So what happens here? R is 1, and as the angle increases and gets closer to pi over 4, what's happening to the r values? They're getting smaller and smaller. So they're basically going to become 0. So you're starting here, and r is big, and then it gets smaller and smaller, and it's going to come tangential to this line. So it's going to come like this. Okay. So now we had 0 here. Now what happens? R values are going to become negative, and you're going to peak at where? Pi over 2, but it's going to be minus 1. So when you're in here, remember, we already plotted this range of angles. Now we are plotting this from pi over 4 to pi over 2. So when you're going from here, all of these R values are negative. So instead of residing here, these R values will flip and go 180 degrees to the opposite side. So they'll be in this region. So instead of being here, they're going to flip and be in this region. Okay. I'm sorry, 180 degrees, not in this region. Okay, because instead of being here, they're going to be here. Okay, so that's 180 degrees on the other side. Okay. No, I was right the first time, my bad, because it's flipped around that side. Because if it's in this, then this angle will be 180 degrees here. Sorry. All right, so let's continue. So what's happening to the R values? They're getting bigger, but in the negative sense, and they're going to peak at pi over 2. So if you were here, so this point here is pi over 2 and minus 1. So in polar coordinates, what would it mean? This would be pi over 2, but instead of being at, because it's negative 1, R is negative 1, you'll flip and come here, so you'll be at this point. So what's happening to my R values? They're getting bigger in the negative sense, and the reason why instead of being here, they're going to be down here, and they're going to look here. Then what happens to the R values? They're still negative between pi over 2 and this is 3 pi over 4 here. So it's this line. Let me just draw a dotted line here. So in this place, So now we are here. When you're going from pi over 2 to 3 pi over 4, you're living here, but because the r values are negative, you're going to flip and you're going to be down here. What are the r values doing? They're going to go back to 0, and because they're going to be 0 at 3 pi over 4, so this is the line 3 pi over 4, you know, this whole line, they're going to come tangential to it and go to 0. Okay. And then the r values are going to get bigger again. They're going to peak at pi, so this is pi here. You're going to be 1 unit there, so you're going to be here, and they're positive, so I don't need to flip. So when I'm between 3 pi over 4 and pi, so I'm here in this area, this is 3 pi over 4 and pi, I'm going to stay there because its r is positive, and r is going to get bigger, and it's going to go like this, and you see it's tangential to that curve, and then r starts to decrease again, and it's at 5 pi over 4, it's going to go back to 0. So this line, if this is pi over 4, this is 5 pi over 4 on this side, and by the way, this is 7 pi over 4, just so you guys know. The reason why I treated as a 3 pi over 4 is because r values were negative, so instead of being up here, they were down here. Okay. So now it's going to decrease back and go to 0 at that point. And then between pi and 5 pi over 4, so we just did that, it went back to 0. Between 5 pi over 4 and 3 pi over 2, it's going to be what again? Negative. So this point is 3 pi over 2 and minus 1. So instead of being here now, this is 3 pi over 2. Because it's negative, you're going to flip and go to this side. Okay. So your graph is going to, between 5 pi over 4 and 3 pi over 2, it's going to be negative. So instead of being in this slot, because this is 5 pi over 4 and 3 pi over 2, it's going to flip and go to this side because it's negative, the r values. So it'll go up and become 1 right here. And then between, this is 7 pi over 4 here, r values are still negative. Between 3 pi over 2 and 7 pi over 4, they're still negative here. So instead of being in this quadrant here, sorry, where are we at now? Yeah, instead of being here, remember this is 7 pi over 4, because the r values are negative, they're going to be up here 180 degrees on the other side, and they're going to go back to 0. So you can start out here, you're going to come back to 0, and then between 7 pi over 4 and 2 pi, it's going to increase and peak at 1 again, so it's going to come back here. This is 7 pi over 4 and 2 pi now, so we stay here because r is positive. So we'll come out here and get this. That's the graph we get. It might seem a little bit complicated, but once you get used to it, once you practice with this method works really well. By the way, this graph has a special name. It's called a rose. Okay, right. So that's how we graph polar curves. Let's take a look at some special polar curves. You should recognize some curves because they're special. Okay. Talk about special polar equations or curves, whatever you want to call them. They're special equations that result in special curves. Okay, so the first one we're going to talk about, and these you should recognize, is called a rose curve. Actually, let's start with a circle. Okay, so there's a couple different ways you can have a circle in polar coordinates. One way is r is equal to some number, let's call it a. Then basically theta can be anything, but r is always fixed at a. So r always, the directed distance always has to be a, but whenever you go all the way around, when theta increases, goes from 0 to 2 pi, r will stay at a. So basically you're going to get a circle of radius 1, a, sorry. Another way we can get a circle is when you have this, r is cosine theta. This gives us a circle, but it gives us a circle to the right. I forgot the a there, sorry, let me put that there. This gives us a circle to the right. This distance is a now, so the radius this time is a over 2. Okay, and another way we can get is a sine theta. So this time again we get a circle, except now it's going up. It's above the x-axis. This is a, this here is a over 2, so radius is a over 2. This one gives us a circle of radius a, this gives us a circle of whatever this number is divided by 2, radius of that. Okay, so these all give us circles. Again, remember these so that way you don't have to plot these, all look them up or plot them on your calculators. You can figure those out easily. And I'll show you how to plot these on your calculators in a little bit. The next one is we'll take a look at the Rose curve. Okay, so that looks like it takes on a couple different forms. So you have r is equal to cosine of n theta, or we get r is equal to sine of n theta. Okay, so now this is a good point to kind of, I just told you we'll take a look at how to graph on your calculator, so it'll be a good time to do that, just to see what these guys look like. Okay, now if, let's go ahead and do that first. Let me show you how to do that. So if you want to graph polar coordinates, the first thing you need to do is go to mode and make sure that, oops, go to mode and make sure that you've selected POL, pole here. Okay, then go to y equal to and type in the polar equation. You can see it says r1, r2, r3 instead of y1, y2, y3, which is what you have in rectangular coordinates. So let's graph cosine of 2 theta. Okay, and then you can go to window and you can set the window. So I'm going to go from 0, theta is my angle, I'm going to go to 0 to 2 pi, so I'll go to 0 to 2 pi. And for the y, for the x min, I'm going to go 2, and for the x max 2, and for the y min I'm going to go 2, and the y max is also 2. So let's graph this. So that looks exactly like what we had when we graphed that rose earlier, right? Cosine of 2 theta, that's what we had. So you notice when it was 2, we got 4 petals. Let's see what happens to this graph if I change the 2 to a 3. Okay, and we can graph it. So we only got 3 petals this time. Okay, so what that is if n is even, we get double the petals. If n is odd, we get the n petals, whatever n is. Okay, so that's what that graph looks like. Okay, and these petals are evenly spaced. Okay, so before I do the sine one, let me do this. So in both cases that happens. If n is even, we're going to get double the petals. If n is odd, we're going to get the same number of petals as n. So like for example, if I have, actually let me do this, let's put this up here. So let's say we want to graph r cosine of n theta or r sine of n theta. We can do a couple examples here. This is 2 and this is 2. So when we did 2, we get this. Okay, so we have 2 theta is equal to 2 pi. So if you out here we have 2 pi, and no, that's not what I want to do, sorry, ignore that. And then if I do cosine of 3 theta, and you can see they're evenly spaced, by the way, they're all spaced by over 90 degrees, you know. Okay, if I do 3 theta, because this is odd, we're going to get 3 petals this time, so it goes like this. Okay, and this time the evenly spaced, this is 120 degrees. Okay, this is 120 degrees, this is 120 degrees, so they're evenly spaced. Okay. So that's how the cosine graph looks like. Let's take a look at the sine one. What does that do? So let's go back to that, change that to the sine function and graph that. Oh, that looks very similar to what we had, except instead of being along the x-axis here, we start, so this is r is equal to sine of 3 theta. So you can see they're still 120 degrees apart, but they're tilted a little bit. So they're going like this. They're still 120 degrees apart. Okay. So that's what we have there. And then over here, what happens when we have 2 theta? Let's see. So we do get 4 petals again, but you can see again they're tilted as opposed to the cosine one is along the x-axis. These are tilted a little. But we get 4 petals. Okay, so that's what those look like. So let me write that down. Note 1, if n is even, then we get 2n petals, and 2, if n is odd, then we get n petals. Okay, and 3, angle between petals for even, it is the angle theta is 2 pi over divided by 2n. Okay, and for odd, if n is odd, the number of petals is theta is equal to 2 pi over n. Okay, so that's how we can figure out the angle between the petals. If you had 3 petals, we'll get 2 pi over 3, which is 120 degrees. If we had if we had odd petals, it'll be that when we had 3. When we had even petals, when we had 2, we would use this. It'll be 2 pi over 4 because n was 2, so we will get pi over 2, which is what the angle between those petals were. It was pi over 2. And same thing over here, if you were to do this, you would see that this is 90 degrees here, so it's pi over 2 from here to here, pi over 2, pi over 2, pi over 2. All right. So the next type of graph we want to take a look at is called, it's a cardioid. Okay, and it looks like this. R is equal to A plus B cosine theta, or we get R is equal to A plus B sine theta. So these are really important. Okay, because you'll see these mostly when you do calculus with polar coordinates. A lot of the examples are cardioids because there are different types of cardioids. That's why I state that. Okay, now it all depends upon whether it's cosine or sine. If it's cosine, it basically means along x-axis. If it's sine, it basically means we're going to be along y-axis. If it's positive, then you go along the positive y-axis. If it's negative, then negative y-axis. If it's positive, go along the positive x-axis. If it's negative, go along the negative x-axis. Okay, so keep that in mind. But there are special cases of the cardioid. If A and B are the same, okay, then we get the traditional cardioid. Okay, so I'll draw one here. So this would be R is equal to 1 plus cosine theta, and because we have cosine, it's along the x-axis, and because it's positive, it's along the positive x-axis. On the other hand, if I had done this, this would be R is equal to 1 plus sine theta. Now it's along the y-axis. And if they were negative, if I had a negative in the middle, then the cardioid would go this way if there was a negative in the middle. So that's all that does. Okay. The second type is if A is less than B, okay, then we get something called a lemma. That's a little tilde at the bottom, okay. What does that look like? Well, we have a loop. Instead of just having um, a cusp there, we have a loop, okay, and then we have the rest of the cardioid is just like what it is. So we have an inner loop basically. So this would be with a cosine, and similarly we could have one for sine, okay. On the other hand, if 1 is less than a over b is less than 2, and by the way, over here we are saying this basically means that a over b is less than 1, okay. So if you divide both sides by b, that's what you get. Then if the ratio a over b is between 1 and 2, then we get something called a dimple. So the dimple looks like this. Again, if we have cosine and a positive, then it will go along the positive x-axis. So the little curve here, a little knot curve, like this. And if it's along that's what it will look like. Okay. Then the last case is if a over b is greater than or equal to 2, then we get a convex cardioid. So that looks like kind of like an egg oblong. Okay, same thing over here. Okay. So those are all the cardioids, and cardioids are probably the most common polar graphs you'll encounter. And then the last special polar graph we want to talk about is something called the lemniscate. So lemniscate looks like this. You have r squared is equal to a squared cosine of 2 theta, or we have r squared is equal to a squared sine of 2 theta. If it's cosine, we actually get the infinite symbol. So this is for cosine. And if it's sine, we get a diagonal infinite symbol. Okay, so those are your special polar graphs that you should recognize. The last thing we want to do is, since we did all this, let's talk a little bit about calculus and we'll be done here. So derivatives in polar coordinates. So what happens if you're given an equation in polar coordinates? How do you find the derivative of that? Okay, so let's take a look at that. So let's say if you're given this, r is equal to f of theta. Okay, and I want to find the derivative. Basically, I want to find dy over dx. Okay, I do know this. Okay, I do know that if this is in polar coordinates and rectangular coordinates, what is that equivalent to? X is equal to r cosine theta and y is equal to r sine theta. So what does that tell me? X is what then? R is the same as f theta, so you get f theta cosine theta, and y becomes r sine theta, but r is f theta sine theta. So what did we do? We started with polar equations, then we had corresponding rectangular equations in essence, and now we basically made it into parametric equations where theta is the parameter. Normally the symbol we use for the parameter is t, so you can think of theta as acting like your t. So why is that important? Well, because we know how to find derivatives of parametric equations. So from section 13.2, we know that dy over dx is equal to dy over dt over dx over dt. That's assuming the parameter is t, but now the parameter is theta. So we'll have d theta, d theta. So now that we have that, we can easily find the derivative, So all we have to do is take the derivative of y with respect to theta. So take the derivative of this with respect to theta. This is a function of theta, this is a function of theta, so we'll have to use product rule. So let's do that. So you get f prime of theta times sine theta, the derivative of the first times the second, plus the first times the derivative of sine, which is cosine theta. Do the same thing. We're going to divide it by the derivative of x with respect to theta. Here is x. This is a function of theta, this is a function of theta, so we'll have to use product rule. So we get the derivative of the first times the second plus the first times the derivative of the second. Derivative of cosine is what? Negative sine. So we get dy over dx is equal to f prime of theta can be replaced. Remember, r is the same as f of theta, correct? So r prime would be f prime of theta. So I can replace f prime with r prime. I get sine theta plus r, because f of theta is r, cosine theta. On the bottom I get r prime cosine theta minus this positive will, because of this negative, will become negative, r sine theta. So here's your formula for the slope of a tangent line or the derivative in polar coordinates. If you're given your curve in polar coordinates, we can still find the derivative. So let's do one example really quick. So let's say find the slope of the tangent line to the curve r is equal to cosine 3 theta at theta is equal to pi over 6. So if you look at it graphically, this is a rose, we just did that, it's got an odd number here, so we get odd number of petals. So somewhere over here there's a line, so this is theta is equal to pi over 6. If you were to draw an angle, pi over 6, 30 degrees. So this is where I want to find the slope of this tangent line here. I want to find the slope of that tangent line. That's what we're doing. Okay. Alright, so let's take a look at it. So we have the formula is dy over dx is equal to r prime, okay, sine of theta plus r cosine theta over r prime cosine theta minus r sine theta. Okay, so we get dy over dx is equal to, what's the derivative of this? That's what we need. Derivative of cosine is negative sine, and the chain rule will give us a 3, so we'll get negative 3 sine of 3 theta times sine theta plus, we just get cosine of 3 theta times cosine theta. On the bottom we'll get negative 3 sine of 3 theta cosine theta minus cosine of 3 theta sine theta. Okay, so now we want to find the value of theta, pi over 6. So let's do that. Because I know that this is the same as the slope of the tangent line, the derivative, so that's what I'm doing. I want to find the derivative at that angle. So I get negative 3 sine of 3 theta. So you have sine of 3 times theta over 6. This will become a 2. I'm sorry, pi over 6. So this will give us sine of pi over 2. We know sine of pi over 2 is 1. Then we get sine of theta. Theta is pi over 6. That's 1/2. Plus cosine of pi over 2 is 0. So because we get cosine of 3 times pi over 6, which will give us cosine of pi over 2, which is 0. So this is going to be 0. So that whole thing is gone. Okay. On the bottom, we get 3 times 1 again, because sine of 3 theta is pi over 2. So that gives us that. And cosine of pi over 6 is square root of 3 over 2. And then again, this will become 0 because cosine of that is 0. We just did that. So now we just need to clean this mess up. On the top, we get 3/2. And on the bottom, we get 3 square root of 3 over 2. The negatives will cancel. And so will the 3's and the 2's cancel. So you'll get 1 over square root of 3, which you can rationalize and write it as what? Square root of 3 over 3. Okay. So let's go back up and take a look at, my picture is wrong because if you look at this, the tangent line's going down, so the slope would be negative. So let's actually take a look at, make sure I did this correctly. If you were to plug in pi over 3 here, I would get pi over 2, which will give me cosine of pi over 2, which will be 0. So r would be 0. Okay. So that's this point. So the picture I drew was completely wrong. So let me draw it nicely so you guys can see that. So imagine we have cosine of 3 pi over 6, which will be the equivalent to cosine of pi over 2, which is 0. So my point in polar coordinates is r is 0 and it's pi over 6. So this, remember I told you before, anytime a polar curve goes to 0, goes to the pole, it'll go tangential to that angle. So that tells me that this angle here must be pi over 6. Anytime a polar curve goes to 0, it'll go tangential to the angle. So my tangent line is the same as this line here because it's going to 0. That's my tangent line. And now you can see it's positive, so that's what it is. You can also, if I have time, I'll show you in class. We can also show that the slope of the tangent line anytime at the pole, it is just the tangent of that angle when it goes to the pole. In this case, it went to the pole at pi over 6, so it'll be tangent of pi over 6. And if you remember from trig, that is square root of 3 over 3. So this only applies, this only works at the pole. At the pole, the slope of the tangent line is just the tangent of the angle for which it goes to the pole. So that's really fast, so you can always do this if you're trying to find the slope of the tangent line at the pole. Okay? Alright, that's all that I wanted to do. You should be able to do your homework from what we've done today. And if you have any questions, as always, come see me.